Hey, good morning, chemistry team. You ready for video number 8 for our thermodynamics journey? It's gonna start getting weird. If you thought it was weird already, it's gonna start getting weirder. All right, we're heading towards a couple videos that are gonna be mind benders, but yeah, we'll just walk through it. I might simplify it a little bit. There's a lot of derivations in the textbook that you can read through if you're interested in, but let's continue the last video. So last video we were looking at Gibbs free energy calculations at standard conditions and using the appendix, the values in the thermodynamic table in the appendix, which I typed a whole bunch of those up for you, put them on my webpage so you can download that on your phone. You can print it out as a hard copy. I'll provide you those on exams and quizzes so you don't have to, there's no way you're going to memorize all that junk. And we were looking at whether you could tell whether a reaction is, spontaneous or not based on its delta G value. And you can look at it at delta G as non-standard conditions or delta G not at standard conditions. So we've only looked at standard conditions right now, which is pretty limited because, you're stuck at 1 bar pressure, or activity of 1 for solutions. So very limited. So ultimately our goal is to look at, hey, is a reaction spontaneous or not at non-standard conditions? Or any conditions really, but non-standard, covers the whole spectrum. Standard would be something, like I said, one particular situation, a defined reference state. We did a problem in the last video where we calculated delta G naught using the appendix, right? The thermodynamic tables. Because it was at 25 degrees Celsius, we could use the tables. If it's not at 25 degrees Celsius, you have to do something different. And we got a value that said that reaction was not spontaneous at that particular temperature under those conditions. And we're like, okay, that's fine. So delta G was greater than 0, right? It was a positive value, which means it's not spontaneous as written in the forward direction. How do you know what temperature that would become spontaneous? That's what we're after in this particular video. So it's a simple question. It's a simple solution. Theoretically, right? But thermodynamics sometimes is theoretically simple, and then you do the calculations, these take forever to do, especially those using those summations, right? It can take a while to mow through your calculations. So I give you lots of space on your quizzes and tests. So here, we want to determine what temperature that reaction flips from non-spontaneous to spontaneous, or vice versa, from spontaneous to non-spontaneous. It's going to be the same temperature. It's kind of an inflection point, right? It's going, hey, I'm not spontaneous, and boom, all of a sudden becomes spontaneous under certain conditions. Now, if you look at those scenarios where if it's exothermic, delta H is negative, and the entropy change is positive, it's going to be spontaneous at all temperatures. So this question doesn't apply. Or if it's endothermic, delta H is positive, and delta S, the entropy change, is negative, they're both not favorable. So it's going to be non-spontaneous at all temperatures, so it doesn't matter. So this question doesn't apply in those scenarios. This question applies in the other two scenarios where the enthalpy delta H, the change there, and the entropy change are counteracting each other. One's favorable and one's not favorable. And so it becomes very temperature dependent. In one of those scenarios, it was more favorable or spontaneous at lower temperatures, and the other was at higher temperatures. So let's take this case. This just gives you a qualitative overview. And then what we'll do is we'll finish up that problem for the last from the last video. All right, so we've got our equation here. And again, this could be at standard conditions as well, right? It's the same equation, just, standard conditions, you're stuck at 1 bar pressure and an activity of 1 for solutions. Let's make an assumption that it's not favorable as far as the enthalpy change, but it is favorable as far as the entropy change. So this is one where the spontaneity is going to be temperature dependent. So this question applies to this. So the delta H is positive, and we'll have that positive delta H. So let's just take a little graph here where we've got the energy on the y-axis and the temperature in Kelvin on the x-axis. We're going to make a huge assumption here for this entire class that enthalpy changes, whether delta H at non-standard conditions or delta H at standard conditions, is going to be temperature independent. All right, so you could actually use the tabulated values in the thermodynamic table to calculate delta H naught at any temperature, not just limited at 25 degrees Celsius. Okay, and we're going to do the same thing for the delta S, so we can calculate delta S naught using the tabulated data in the thermodynamic tables to calculate it at any temperature. We can't do that for delta G though. Again, this is an assumption that's going to make our lives a lot less miserable. So let's say delta H, regardless of the temperature, is just this straight line going across. Remember, what we're doing is we're comparing the delta H term to the T delta S term. That'll tell you whether something's spontaneous. And if delta G is greater than 0, it would be non-spontaneous as written. And if delta G is less than 0 or negative, it's spontaneous as written. We derived that from the second law of thermodynamics, right? So this is a scenario. This green line here is the T delta S line, the temperature in Kelvin, the absolute temperature times the entropy change. So if we're taking delta S as constant in this scenario, so as we increase the temperature, the T delta S will go up, right? So that's that increasing because the temperature is increasing from some lower value to some higher value. Whereas delta H, that doesn't have a temperature term in it, so it's going to be straight across. If delta S is positive, right, then the T delta S term is going to be negative, and delta H is positive. So take a look in this purple section right here. In this scenario, the T delta S term is less than the delta H term. Everybody agree? So if delta H is positive and the T delta S term is negative, but this term is less than that, then delta G would be positive in that scenario. So let me grab a pen here. Let's see, what's a color we haven't used yet? Let's use red. So in this scenario, delta G is going to be positive. So here, delta G is greater than 0. Okay? In this whole region right here, because the delta H term is bigger than the T delta S term. All right, which means delta G would be positive. Now, delta G is greater than 0. That's not spontaneous. All right, so let's write that down. That'll be non-spontaneous. So that region right here would be not spontaneous. Any temperature that gives you a value below this line right here. Okay. Now let's say we increase the temperature. Increase it, increase it, increase it. And you see that inflection point right there? Right there. That's the point we're looking at. To be able to answer this question, what temperature does go from non-spontaneous to spontaneous, that is the temperature we're looking for, because that's where it flips from a positive delta G to a negative delta G. All right, so at that temperature, delta G would be, let's see, what's in between a negative delta G and a positive delta G? 0! Right, so at that scenario, delta G, I have trouble drawing my G's. At that point right there, your delta G is 0. Or if we're doing standard conditions, that'd be delta G naught. All right. And if we keep increasing the temperature, now the T up here in the red area, the T delta S term is bigger than the delta H term. And if the T delta S term is all negative, because delta S is positive, and delta H is positive, then this region right here, delta G is less than 0, right on, because the T delta S term is dominating because you're at higher temperatures. And that would mean spontaneous. See that? You know, not critical to have this, but it gives you kind of an overview of why we're using that point. So when we're going to answer this question, like in a part A, calculate delta G or delta G naught, right? And if you get an answer that is positive, it's not spontaneous as written. Well, there's an obvious part B that says, well, what temperature would it become spontaneous? All you do is take this equation and plug in 0 for delta G. Hey, then you solve for your delta H and delta S, right? And we can't do that now for non-standard conditions. We haven't learned how to do that. But if we're at standard conditions, we're assuming those are temperature independent. We could use the tabulated data from the thermodynamic tables. Calculate your delta H, which will take a while. Calculate your delta S, which will take a while. Solve for T. What temperature would it take to make delta G 0? So at 0 is when it goes from spontaneous to non-spontaneous. So let me erase this board. We'll write that problem up from the last video. I'll just write the answer down that we had at 25 degrees Celsius, and then we'll calculate what temperature would it become spontaneous. Be right back. All right, guys. So here's what we had from the last video. We did part A of this. So we had this reaction where we had the magnesium oxide solid plus carbon graphite solid going to magnesium solid plus carbon monoxide gas. And we went through and it asked us before what was is it spontaneous at 25 degrees Celsius under standard conditions. So because it was standard conditions, we could use the back of the book with the thermodynamic tables. We calculated delta G naught at 25 degrees Celsius. We actually found out it was 432.2 kilojoules per mole at 25 degrees Celsius. Remember, it's got to be at 298.15 or 298 Kelvin, 25 degrees Celsius to use that back of the book for delta G. That's definitely bigger than zero. It's a lot bigger than zero, so definitely not spontaneous as written under standard conditions. All right, we'll change that to non-standard conditions later. It gets a little weird. So this will be an obvious part B. What temperature does it become spontaneous? All right, so we talked about that with the graph earlier. So here's kind of a straightforward four-step process, but it's going to take a while to calculate. All right, so from the last video, we had delta G naught's 432.2 at 25 degrees Celsius. That has no relevance to this problem. That was just part A telling us that's not spontaneous. So we want to know at what temperature does this delta G value become zero? Because that's the inflection point where it goes from non-spontaneous to spontaneous, or if you look at that plot we had earlier. So what we're going to do is we're going to plug in a delta G naught value of 0, or if you're at non-standard conditions, it'd just be delta G. Step 2, let's calculate delta H, because remember, we're using this equation here, delta G. In this case, we're doing standard conditions. It's delta H. I don't have a lot of room here. Minus T delta S. Right? We're at standard conditions here. So what we're going to do is we're going to plug in a 0 for that. Okay? That's going to go to 0. That's the trick to this problem. If you don't do that, you're toast. We're going to calculate delta H naught from the tables, assuming temperature independent, or even though we won't be at 25 degrees Celsius, we're going to assume delta H naught is constant at all temperatures to make our lives less miserable. We're going to do the same thing for delta S. We're going to assume that we can use those tables at any temperature. It's just delta G we can't. All right, so step 2, calculate delta H from the tables. Step 3, calculate delta S from the tables. Well, in that scenario, we would have delta G naught, delta H naught, delta S naught, and then we can solve for the temperature there, right, in that last step. So it's a multi-step calculation. If you feel motivated, pause this video and go ahead and do that. Give me the delta H naught from the tables. Give me the delta S naught from the tables using this. Pretty simple. They have all coefficients of 1, similar to what we did in the last video for delta G. Plug it in and solve for the temperature. I didn't specify the unit, so you could do it in Kelvin, degrees Celsius, degrees Fahrenheit, or Rankine if you're feeling really nerdy. What the heck's Rankine? Go Google that one, temperature Rankine. But since it's not specified, just leave it in Kelvin because that's what's going to spit out from this. Have at it, gang. All right, how you doing? Hopefully you finished it. I'm stuck on my board space here. So anyway, step 1, we're plugging in delta G naught value of 0. That's the easy part. That's our inflection point where it goes from non-spontaneous to spontaneous. Then we're going to use the tables in the back of the book. Remember your thermodynamic tables. Ho ho! So same equation for delta G reaction, delta H naught reaction, delta S naught reaction. It's just here we're taking the sum of the stoichiometric coefficient times the standard heat of formation for the products minus the same thing for the reactants. So we got 2 reactants and 2 products. So we have 2 terms on each side. We did the same thing for delta G, right? So we're going to take 1. And again, this book doesn't use the units of moles in there, so we'll end up with kilojoules per mole of reaction. If you put moles there, you'll end up with just kilojoules. I've seen different books do different things. Not a big deal. All right, so we're going to take 1 times the value of the magnesium from the table, plus 1 times the value for the carbon monoxide, standard enthalpy of formation. And we're going to subtract from that 1 times the standard enthalpy of formation for the magnesium oxide solid, plus 1 for the standard enthalpy of formation for graphite. All right, so let's look up the first one, magnesium solid. Now, if you really understand what you're doing, you got to understand the definition of the enthalpy of formation is what's the energy change when you form exactly 1 mole of a substance from its elements in their standard states. So if you're forming an element, if you're forming 1 mole of an element in a standard states from 1 mole of that element in its standard states, it's the same thing on both sides of the equation. It's got to be 0. So elements in their standard states are 0 for delta G naught and delta H naught, not for the absolute entropy though. So if we look up magnesium, we saw that earlier with delta G, the delta H formation is 0, delta G formation is 0, but the entropy is not. So that's going to be a value of 0. If you know that, you save your time on a test or quiz flopping around through that stupid sheet, right? Just go, oh, it's an element in standard state. Boop, 0. Now, carbon monoxide is not an element in the standard state, so that's going to have a non-zero value. So let's look up carbon monoxide. So look under C for carbon. We're in the first column this time for the molar enthalpies of formation here. So carbon, we want carbon monoxide gas, which is right, not carbon dioxide, carbon monoxide gas is negative 110.5 kilojoules per mole. So again, carbon monoxide gas, negative 110.5 kilojoules per mole. And that's why I put negative 110.5 kilojoules per mole. And we have a coefficient of 1. If that had been a coefficient of 3 there, I would have put a 3 there. Right on? All right, so that's our product term. That's our final state. Minus our initial state, our reactant. So we take 1 times the enthalpy of formation of magnesium oxide. So that's a compound, so that's going to have a non-zero value. So let's look up magnesium oxide solid. So there's magnesium, that's magnesium carbonate. There's magnesium oxide solid. So that's going to be negative 601.7 kilojoules per mole. So that's why I have negative 601.7 kilojoules per mole. And then 1 times the graphite. And remember, graphite is the allotrope that is the most stable form. So if you look at carbon graphite, you'll see the value of 0 there, right? Boom. Not diamond, graphite's 0. So I plugged in a 0 there. So obviously putting these terms together, that's nothing, 1 times that. So that's just negative 110.5 kilojoules per mole for the product term. And over here, 1 times that, that's 0. So our reactant term is negative 601.7 kilojoules per mole. That's easy. Obviously, if we're subtracting a negative makes it positive, we're going to have a really big positive value for delta H here. So negative 110.5 kilojoules per mole minus negative 601.7 kilojoules per mole, both to 1 decimal place, gives us 491.2 kilojoules per mole. That is our delta H naught reaction, assuming temperature independency. All right. Because remember, we're not going to be at 25 degrees Celsius here. We're trying to calculate what temperature does this become spontaneous. So we've done step 1, step 2. Now do step 3. Do exactly the same thing, but for the entropy, because we want the delta S naught for that reaction. And once we have that, then we can plug everything into our equation and solve for T. So we're going to have the same thing. The only difference, you're going to have the absolute entropies there, right? Because of the third law of thermodynamics, we don't have to have delta S. We can just have S because the reference state is 0 for a perfect crystal at 0 Kelvin. Nice. So I'm going to erase this. You pop out delta S for me. See if you get what I get. How'd you do on your entropy change? Did you get what I got? All right. So we've got the exact same reaction, equation again. We're just using the absolute molar entropy there. So we're going to take 1 times the product, Mg solid, plus 1 times the product, CO gas. Put that in brackets. And then subtract 1 times the magnesium oxide solid entropy, plus 1 times the graphite. So products minus reactants, put the products in brackets, put the reactants in brackets. Same thing every time for delta G, delta H, delta F. You gotta love it. Very simple. Tedious, but simple. All right, so let's look up the values. And remember, these are not going to be, none of them are going to be 0. Okay, so let's look up the entropy for magnesium. Where's magnesium? See the zeros for the other ones there, but it's 32.68 joules per mole Kelvin, right? Not kilojoules. Delta H and delta G are kilojoules, but S is joules. Got to watch out for that. It's going to bite us in the butt if we don't watch that. 32.68. That's why I put 32.68 joules per mole Kelvin. Well, let's look up carbon monoxide gas. It's a gas. It's got a bond. You'd expect that to be a little bit higher than magnesium. This is the third column, so let's look up carbon monoxide gas right there. Go across to the third column. Assuming I can see 197.7. See the 197? So carbon monoxide gas. Go to the third column, 197.7. So I have 197.7 joules per mole Kelvin. My biggest mistake is I'm reading across like this and I go, and I go to the one below it. I'm like, oh, fart, man. It's a bummer. I did it right on my test. How can you give me a 0? Oh, you put the wrong number in. That's why I give you lots of partial credit. You do this all right, just put the wrong number in there. I'll give you most of the credit. Although in the real world, you probably just killed somebody or, had a building collapse or something. You got to make sure you don't make those mistakes in the real world. Okay, but on a test, crap happens. So I understand that. All right, let's look up 1 times magnesium oxide solid. Where'd my table go? Where's the magnesium oxide solid? Right there. And that has an entropy value of 26.94. Boom, joules per mole Kelvin. And then graphite, I wouldn't expect that to be much, but let's look up carbon graphite. And that goes across, boop, 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 5.74, baby. That's why there's a 5.74. So let's take our products, add them together. So take the 32.68 times 1 plus the 197.7 times 1, right? If that had been a 2 here, I would have multiplied that by 2. Watch out for those coefficients. Good to 2 decimals, good to 1 decimal. So I'm limited to 1 decimal place. So I get 230.380 joules per mole Kelvin, good to 1 decimal place. Do the same thing for our reactants. Let's take the 26.94 times 1 for the magnesium oxide solid. Add 5.74 times 1 for the graphite. Put those together, both to 2 decimal places. So my answer is 32.68 joules per mole Kelvin. Now we can take the products minus the reactants. We're good to 1 decimal place here in the products, 2 decimal places in the reactants. So our answer is limited to 1 decimal place. And I get 197.7 joules per mole Kelvin. Hopefully that makes sense because you have no gases in your reactants and you have a gas in your product. So delta S should be positive. That's a large increase in the available microstates because of the translational motion and vibrational motion of the carbon monoxide gas. You got to thank Boltzmann for that one. All right, let's do step 4. We got delta S naught, we've got delta H naught, we've got delta G naught, which was assigned a value of 0. Solve for temperature. Let's see what temperature this becomes spontaneous. This is the easy part. Watch out for the joule to kilojoule conversion, right? This is joules. Your delta S is in joules. Your delta H is in kilojoules. You don't put your units, you're going to get caught with your pants down. Got to be careful. All right, let's see how we do. Step 4, solve for the temperature and when this non-spontaneous process at 25 degrees Celsius under standard conditions becomes spontaneous under standard conditions. It'll only be 1 temperature when this happens. And again, we're restricted to 1 bar, 1 atmosphere pressure. So here's our equation from thermodynamics that we derived earlier. We're plugging in a value of 0 for delta G naught. We're solving for T, so I like you to isolate your variables. It's so much, it minimizes mistakes and it's for you. And it makes it easier for whoever's reading your work because they don't have to do all the algebraic manipulation themselves. All right, so I'm going to move T delta S to the other side. So if that's 0, add T delta S to both sides. So T delta S naught equals delta H naught. Divide both sides by delta S. So T will be delta H naught divided by delta S naught. I see a lot of people get those upside down. Work on your algebra, please. All right, so T is delta H naught over delta S naught. So what was our value of delta H naught from that? Was that the 491.2 kilojoules per mole? So 491.2 kilojoules per mole. Please put your units. I'll show you where it'll bite you if you don't. Now you're dividing by delta S, which means you can multiply by the inverse of it if you want to keep dimensional analysis going and do a unit line equation. So delta S was, what was that, 197.7 joules per mole Kelvin? So 197.7 joules per mole Kelvin. That's the problem with entropy, is that joules. You can see the moles cancels out. And if you had done your delta H and delta S with moles for your stoichiometric coefficients, you'd end up with just kilojoules and joules. There would be no moles in here, so not a big deal. It's the same effect in the end. But note, kilojoules and joules don't cancel out. Huge quantities of students undergo mass destruction on exams because they get sloppy because they're in a rush and they don't put their units in there and they leave it like this and their answer's off by 1,000. Happens to a lot of people. Don't be lazy with your units, my friends. We got to convert. Whoa, that's red. We got to convert joules to kilojoules here. So let's do our joules to kilojoules. I would expect you to know those simple metric conversions off the top of your head. So I won't be providing you that. All right, kilojoules cancels kilojoules. Joules cancels joules. The only unit we have left is Kelvin. Hey, it didn't specify a specific unit for temperature, so let's just leave it in Kelvin. Hey, if you finish the quiz or test early and you want to show off, convert it to Celsius, rock and roll. But if you screw that, you're going to miss points. So just leave it in Kelvin. We got 4 significant digits in our enthalpy change. We got 4 significant digits in our entropy change. The metric conversion's exact, so we're going to get 4 significant digits in our final answer, which will be in Kelvin. I get 2,484.57 Kelvin. So that's closer to 2,485 than it is to 2,484. So I'm going to round that up. Notice I haven't rounded anything until the very end. So 2,485 Kelvin. That is how much you'd have to increase the temperature for this reaction for it to become spontaneous. So not a good business model, because the amount of money it would cost you, right? Your overhead expenses for maintaining that temperature would be horrible. And there's some reactions where the temperature is so high, it doesn't make any sense, right? You might not be able to have the substances exist at that temperature, right? So anyway, but theoretically, it's a fun equation to do. It gives you a rough idea of how to calculate stuff. So that was a good problem. But we're going to move on in the next video to relating what we did for the last, I don't know, 4 or 5 chapters on equilibrium. Ultimately, we want to relate and connect equilibrium to thermodynamics. This is going to be a crazy but cool video next. Have fun!